Hi again, everybody, and welcome. Today is Wednesday, May 19th. We are basically almost done with this class, so today is going to be finishing basically chapter 31 and doing some problems from chapter 31. Actually, we're going to focus mainly on the RLC circuit, of course. And then I'm hoping by Monday of next week, we will get chapter 32 also out of the way, chapter 32 in terms of concepts only. And then we will be doing basically applications. Monday, a week from this Monday, there is no class because that's a holiday. Since because we're going to do the applications, and we just had a discussion from another class, actually similar to your class, class 4C, actually, some of you are probably in that class, where we planned not to basically meet during the lecture time, which is only an hour and 25 minutes early. Instead, for doing applications, because there will be, today is the last lab, by the way, too, okay? So we will have plenty of time to do problems during the lab session where we can go in far more depth in it. So in other words, we can, since the lab session is a little over 3 hours, we may not spend the entire 3 hours basically together, but at least do not have any constraint on time and basically discuss at least the problems and thoroughly and go through them. So on Wednesdays, starting from this Wednesday, after this Wednesday, of course, is that we will be meeting at 2 o'clock instead of noon, and then end it whenever we decide to end it. If at 4:30 we decide, you know what, we have had enough, basically we don't want to take it anymore, so we can stop. Because we're going to be doing applications, we're going to be doing mainly problems. So this is a suggestion that was I made actually for my physics 4C class, and they welcomed it. So I'm hoping that also you guys would work with you guys this way. Because if we meet at noon and then we are doing only problems, by the time we barely have an idea or two going through, at that time we'll break. And then when we meet again, though, the thing loses a little bit of its efficiency, and I don't know, it feels like kind of a disruption. So we probably should meet at 2 o'clock, and whenever we decide to end it at that point. But the Monday, because the Monday 31st, there is no class. The Monday 24th, we have a regular class, so we're meeting on regular time on Monday at noon. And the Monday after that is exam time anyway, so there is no more Monday. So the only times really left after this Monday are the Wednesdays. So this is the suggestion I'm making, and hopefully you guys are okay with it, okay? So having said that, we still are not done with chapter 31, okay? So let me jump into the stuff that we did with chapter 31. We did everything that needs to be done, honestly. There is a big discussion that needs to happen on the resonance, because this is the time when we have to understand what resonance is. So we really have to get that out of the way. And then we're going to do problems anyway. Okay, share screen. So last time, basically, I was able to find the power, and the power, of course, is expressed in terms of the potential, and in terms of the potential times the current. And I can express them with a quantity called the root mean square. So what is the root mean square? It's basically you square the quantity and then you take its average, which is defined as 1 over the period time, the integral over the entire period. And then you take the square root. So it's in the words actually itself. So the RMS is exactly in the words. Well, how do you operate? I mean, how you do this? The root is the last operation. The mean is the second operation in the square. So when we had a signal that was sine or cosine, I know I started with sine, but I could have done a cosine too. So when you have a cosine, omega t, for example, and you would want to find this RMS. So what you do in here, you first square it, because that's what the S stands for. And then you find its average, which is you integrate it over a whole cycle, and you divide by the entire cycle. That is what the average in this case. So that is what the M stands for, the mean, this whole operation. And then the root stands for taking the square root in this case. It turns out that this value turned out to be exactly 1/2, okay? Because I know I did it for the sine, but the cosine is no different than the sine, actually. Did we do it for the cosine or the sine? Let me make sure. I think it was the sine, yeah. At some point, we have a sine squared, okay? Cosine phi is constant, so it comes out of the integral. let me make this is today, okay? So that today is 5/19. The discussion before was on 5/17. Anyway, so if we did the cosine, it's going to be the same value because there is an identity in cosine of 2 alpha. I used the first time 1 minus 2 sine squared of alpha. I could have used cosine squared of alpha minus 2 cosine squared of alpha minus 1. It's the same thing, okay? Because all you have to do is just use sine squared plus cosine squared is equal to 1, and you'll go from one to the other. So that gives me a way of finding basically this quantity, which is cosine squared of 2 of alpha, namely alpha in this case is omega t. And that means that cosine squared of omega t is equal to, according to this expression, move the 1 to the other side. So it's going to be 1 plus cosine of 2 omega t over 2. And when you integrate over a whole period, the lower limit is going to be, first of all, when you integrate, the cosine is going to be a sine divided by 2 omega, of course, omega t, evaluated between 0 and the lower limit is 0 anyway. And the upper limit is t, and the 2, sorry, there is a 2 in here. And the upper limit is 2, t, so it's going to be 2 times omega t, and omega t is actually 2 pi. This quantity is 2 pi, because remember, omega and 2 pi are related to one another through this expression. So when you multiply them by themselves, it's going to be 2 pi. So the whole thing is going to be sine of 2 pi, 4 pi, and sine of 4 pi is still also 0. Sine of 0, sine 360, sine 460, this is 460 degrees, okay? So it's still 0. 460, 360, 720, sorry. But it doesn't matter, it's 0. So the only thing that's going to be left is 1/2. So it's identical to the other. So the other matter, the only difference is this sign changed from a negative to a positive, because if we go back through the previous calculation, I had a minus in here. And I said the upper limit is 0 and the lower limit is 0. That's why this doesn't contribute, because at the end, you're averaging a function that is at some time positive and sometime negative between its cycles. So you're going from, let's look at this function, okay? You're averaging it. So it's here, it's positive. The period, by the way, of this one is half of, it's 2 pi divided by this whole number. So the period of this function, 2 omega t, is actually 2 pi over the multiplier of t. That is the actual frequency. The multiplier of t in this case is 2 omega. So as a matter of fact, this is periodic, and periodicity is pi over omega, which is half of t, because pi over omega from this expression is t over 2. So this is actually of a period t over 2 in terms of time. So in half a cycle, it comes back. So this side in here is t over 2, the actual t over 2. So it repeats again one more time for the next t over 2. So basically, I ended up with 4 values, that's all. This is positive. This whole thing is negative, which is twice as much as this one. But this is twice as much as that one, so it cancels this. And now this one is actually twice as much, but this one and the other one will be the same amount. So at the end of the day, it's going to be 0. But sometimes it's positive, sometimes it's negative, and it cancels out. So that's what the interpretation of this integral being 0. Because the integral is just the area between the curve and the y and the x-axis, and this area is sometimes positive, sometimes is negative. That's all. So this integral sometimes positive, sometimes negative. That's why this average is 0. However, the average of 1/2 is exactly 1/2, because you integrate from 0 to t of 1/2. That gives you 1/2 of t. But don't forget, you have a t in the denominator. So you'll have t over 2 divided by t, cancels the t's, and you'll end up with square root. I'm sorry. 1 over square root of 2, the RMS, not 1 over 2. It's not 1/2. There is a square root of 2. Did we do it correct in here? Yeah, we defined it with square root of 2. So the RMS has square root of 2. In other words, the voltage is 120 volt times square root of 2, which is 170 volts. So that is basically, in a nutshell, the thing with the RMS. Now, if somebody gives you a different signal, and it is possible that there is this square signal, for example, that repeats every p period, then in this case, this is the period. This whole thing is t. and this is T over 2. And let's say, for example, it's my maximum value. I'm doing the voltage. This is V max. This is a periodic signal still. So I'm going to do 1 over T, the integral from 0 to T of the square of V sub T. This is the V sub T squared times dt. Obviously, this V squared of T is only valid between 0 and T over 2. Otherwise, the other value is equal to, so the integral from 0 to T halves is going to be V naught squared dt plus the integral from T over 2 to T, and that is equal to 0 squared dt, because clearly from this signal, you can clearly see that it is 0 in this section. So this is a square signal. So if I want to find its RMS, I proceed in the same fashion. I square it first, and then I divide by and integrate from 0 to T, and then divide by T, and take the whole square root when I'm done with this. Okay, don't forget the square root when all this is done. So obviously this integral is 0. This integral now is V naught dt, so just T over 2 times V naught. So this whole thing again is 1 over T times V naught squared over 2. And in this case, if you look at this expression, first of all, times T, because you integrate this constant, T cancels the T, and it's V naught squared over 2. When you take a square root, remember the RMS has R in it, and that R stands for the square root. It too is V naught over square root of 2. But this is not always true. You may have a different signal, where actually it's, for the most part, it's V naught, and then at some point, only for small sharpener, it dies out, and then it picks up again. So in that case, the boundaries of integration does not go from 0 to T over 2. It could be, for example, 2/3 of a T. So if it's 2/3 of a T, then in this case, the boundaries of integration will become to 2/3, and this is from 2/3. And this expression here becomes a little different. So in this case, the boundaries of integration are from 0 to 2. So it's going to be 2/3. Okay. And this will become 2/3. And the effective RMS in here will have square root of 3 over 2 in here in it. Okay. So the RMS in here, in other words, can be different. It's not always square root of 2, depending on the actual signal you're trying to RMS. Okay. Trying to find its root mean square. So again, the power supply could have any kind of form. It doesn't have to be a sine function. It could be like this, or it could be like this, growing linearly and then drops. Then another cycle grows linearly and drops, and so on and so forth. It could be as a matter of fact, any weird shape in here, okay? Okay, as long as you have that, you can integrate, as long as it's periodic though. If it's not periodic, you can't have this defined that way, okay? So you can integrate it and find the root mean square for it. Does this make sense? At least the RMS. Okay, very good. Did you guys do this in math already, in calculus somewhere? Yes, no, maybe? Okay. If you didn't do it, this is probably your first exposure to it. You're going to see it a lot in physics. I mean, I can tell you, for example, when you take physics 4D, namely quantum mechanics, and you're going to deal with a particle in a box, which is really a very important problem in physics, which has application in chemistry and everywhere else. And it gives you the first time exposure to a quantization of energy levels in quantum mechanics. It's actually the same way. This is the calculation for the normalization of the wave function. There is exactly this integral, the sine squared. That's exactly the same integral. So you saw it in here, so probably you're going to have no problem with it there. Anyway, there is another place that, chapter 32 also will deal with it. Okay, chapter 32 will have a solution for Maxwell's equations. And remember, the electric field is going to be squared. The magnetic field is going to be squared. Oh, man. Did it pause? Is my internet lagging or something?
Yeah, the screen is just frozen.
Is it still frozen?
I think it's good now.
Okay. Anyway, when we do chapter 32, we also are going to need this expression because, like I said, we're going to average the energy density for the electric field and the magnetic field, and we will have a sine squared there or a cosine squared, and I'm going to remind you it's 1/2. Okay, when you did the physics 4C, also to some extent we didn't go through it in detail, but also when we do the energy density on a string or the energy density on standing waves actually, or anything else, you're going to have the sine squared again. So this expression is a common expression available everywhere else. So RMS, square the thing first, take the average second, and do the root at the end. Okay, and this is what you deal with on a daily basis in your household. The 120 volt is actually an RMS. In other words, an effective voltage. You know, and I know that the voltage is going up and down. And it's not going up and down between 120 and negative 120. It's actually going between square root of 2 times 120 and negative 120. It is 170 up and down. Okay, so enough said about that. Let's look at the current again, because it's very important to see what's going on with the current. The current was, this is, I'm already talking about the maxes or the RMSs. There is only square root of 2 difference between them, that's all. So if I write I, dress it with whatever you like, max or RMS. There is, you divide this one by square root 2, you divide the other one by square root of 2. Divided by Z. Remember, Z was equal to R squared plus, I can write it in different ways now. I know this, it's XL minus XC squared. That's one way of writing it. That's good. Or I know XL is equal to omega L. I'm writing omega now. This is actually, I know I wrote omega prime, just to make a distinction. But from this point on, we're just focused on the steady state. Meaning, we don't deal with that square root of omega naught squared minus lambda squared as being omega. We don't need really omega naught, but we keep omega naught in mind. Omega naught still 1 over square root of LC, but we don't deal with the transients that have that square root of omega naught squared minus lambda squared, where we said that was our omega. So ignore that for a moment, so that we don't write the prime in here, okay? Because this is actually the driving voltage. Frequency. It has nothing to do with the transient. It's really the steady state. Okay. Same thing. XC was 1 over omega C, where this omega is the same omega as this one. So there is a frequency that you're going from the voltage, which is 60 hertz in the United States, or 2 pi times 60 in the United States. Okay. So that is the omega I'm talking about, not the. In other words, so there is a slight change of symbols in here so that we don't write that omega prime continuously. Okay, or if you wish, change the prime with it. So make the other one prime and keep this one in prime, because it was important then because it was the only thing in town. Now there is a new boy came in, so the other one is demoted. Okay, so that is one thing. The other thing also, we found that there is a phase difference that is given by the tangent of phi equals to XL minus XC over R. Here is a deal with this phase difference in here. I know we started with the current. The current was sine omega t plus phi for the current. Okay. The voltage, I'm assuming it has no phi in it. Phi equals to 0 in it. Okay. So here is the situation here. The voltage across the inductor was equal to L times the derivative of I with respect to time. If I take the derivative, remember, the sine, I dropped the omega, and that's how we got that omega in the XL. And then I changed the sine into a cosine, and the cosine, when it became a cosine, I made it that so that it's a sine plus 90 degrees. So this ended up being plus 90 degrees. So this is ahead of the current. So every time the voltage is ahead of the current, I know that this phi is positive, and in this case, overall, this guy is winning, XL is winning. So even if phi is not equal to 90 degrees, and it is not necessarily always 90 degrees, then in this case, I know that this is an inductive circuit, that it's led by the inductor. If, on the other hand, this value turned out to be negative, that means XC is winning. And in this case, I'm dealing with a capacitive circuit. So if I try to plot that function as a function of omega now, think of it this way. Your signal is changing with omega. I mean, changing omega for it. Then phi will change accordingly for very large omega. What I mean by large is, let me write the tangent again, okay? Tangent of phi. It's omega L minus 1 over omega C divided by R. I can divide everywhere by omega C, and I write this expression as follows. Tangent of phi, or actually divided by L, it's much better, okay? So what I will have in here, I will have omega as a common factor, and the L as a common factor also. I will have 1 minus 1 over omega squared, because I took omega out, LC, divided by R, okay? That's good. That's one thing. Or I can take this 1 over omega C as a common factor, which is actually preferred, honestly. Tangent of phi is equal to omega RC, and then I will have omega squared LC minus 1. Either way, okay? It doesn't matter. I know LC is just 1 over omega naught squared, because remember, omega naught is 1 over square root of LC. So this is going to be actually written as tangent of phi is equal to omega over omega naught, the whole thing squared, minus 1 divided by, and in here I have an R. All I have to do is multiply by L and divide by L in the same time. So we'll have an L in here divided by R, okay? And I will be left with an omega. Oh, I'm sorry. That's not good. That's not good. So we have to take also the square root in here of C and the square root of L, and leave this one as square root of L. Basically, what I'm trying to say in here is once you have that, it's going to be L and square root of LC is C in here and square root of L in here. The point being in here, I need omega over omega naught. Okay, remember omega naught is just 1 over square root of LC. That's it. So what I did in here is I tried to get this thing as dimensionless as possible, and it is dimensionless now if you work with it correctly. 1 over square root of L over C. If I'm not mistaken with the calculations, please check it for me. And that when I'm left with in here, I'm going to call this one x squared minus 1 over x, where x is actually the ratio of the frequency over the natural frequency of the circuit. So it's clearly for very large frequencies, when omega is very large compared to omega naught. In other words, when x is very large compared to 1, which means that omega is very large compared to omega naught, then in this case, 1 is neglected, and the tangent of phi will be simply x, proportional to x. I know that number in there is fine. That's fine. That's a constant. If that's the case, then in this case, x, the tangent is very large, and that means that the phi approaches pi over 2. And that is difficult because that's when the inductor is winning. When, on the other hand, x is very, very small compared to 1. That means it's extremely small. In other words, omega is extremely small compared to omega naught. Then in this case, this number cannot be, as a matter of fact, it has to be neglected in front of 1. So the tangent will become, tangent of phi becomes a negative number because x squared is neglected in front of the 1. So I'll be left with negative that number there, which I'm not, I mean, it's a constant anyway, times 1 over x. In other words, also, this one will blow up, but it'll blow up in the negative direction. And I know then that's the phi is actually going to be a negative pi over 2. So in other words, this is how the function looks like in here. For very large x's, this function approaches 90 degrees. For very small x's, it approaches negative 90 degrees. And in between them, when x is exactly equal to 1, namely omega equal to omega naught. When x is equal to 1, namely omega equal to omega naught. At that point, the numerator is exactly 0. X squared minus 1 is 0. And this number is just omega naught at that point. So the tangent of phi is equal to 0. And that means phi is equal to 0. So this is the point, the turning point And that point is at exactly omega naught. So this is omega that is changing now. If I write it as x, it's 1. If not, it's if it's omega, it's omega. So for low frequencies, it's negative. Then it goes through this 1, and then it behaves this way. So this point in here is called resonance. So omega equals to omega naught. But in this case, this quantity is 0, in which case z is equal to r, because xl is equal to xc at that point. So z is equal to r at this point. The other two are canceling one another. So that is basically how I understand resonance in terms of phase. So they are 90 degrees out of phase at very high frequencies and very low frequencies, but they are exactly in phase, namely phi is equal to 0 at resonance. So that is one thing to look at this problem. Another way to look at it also is in terms of the current itself. I, remember, is equal to V over square root of R squared plus, again, I'm going to write it omega L minus 1 over omega C. So the whole thing squared under the square root. I'm going to do a similar manipulation of this expression by getting 1 over omega C out. So here is what I'm left with. I is equal to omega C in the numerator, because I'm taking it as an omega C squared in here, times V over, if you wish, I'm multiplying by omega C in numerator and denominator. So I'll be left with square root of R squared, omega squared times C squared, okay, plus, did I multiply by, yeah, plus when I bring it inside, it's going to be omega squared times LC minus 1. The whole thing is squared, okay? So it looks similar to the first one, except I need also in here, out of one of the C's, I need just one of them. So I will be left with a C, and I need also an L in here, and I'd have to divide by that L. And let me tell you why. Because this is actually omega naught too, when I do that, okay? So if that's omega naught squared, that is, okay? So what I'm left with, except it's in the denominator, because this is 1 over omega naught. So when I'm done with that, this is actually 1 over omega naught squared too. So when I'm done with this operation, this is how the expression looks like. I is equal to, and again, I'm going to do something similar in here. So I'm going to break down the square root of C into 2 quantities. Square root of C in here, and 1 over, leave the other square root of C in here, and divide by square root of L, and multiply by square root of L. This is basically known as trying to get your unitless things, trying to normalize your expression to become without units as much as possible. So the numerator in here looks like this then. Square root of C over L times V times omega divided by omega naught now in the numerator divided by square root of this quantity, which is R squared times C over L times omega divided by omega naught squared plus, again, omega divided by omega naught, the whole thing squared minus 1 squared. Now I'm ready to go to the calculator, because all I have to do is call again omega over omega naught as being my X. And I'm going to call this quantity in here, as just being number R, little r, okay? Because this is mainly the resistance in here, square times C over L. So if I do that, this is how the function, and divide this whole thing by this number. So this is how the current looks like. It's an I divided by that number in here, square root of C over L times V, which I'm going to call Y, is times X, because I have an X in the numerator, divided by square root of little r squared, or little r, let's call it r squared times X squared plus X squared minus 1, the whole thing squared. This is the function I want to plot really. Okay. So let me stop sharing and share with you the calculator. Where is the calculator? Or it's a graphing calculator, actually. So let me write these functions. This function is a radian, so we don't have to worry about anything in it. So let me go to the graphing capabilities of this function. Again, the function I want to draw is the function y equals to x over square root, open parentheses now, open another parentheses, x squared minus 1 the whole thing squared plus r squared, that's fine, r squared times x squared. This is the function I want to plot, and let me make sure I have all the parentheses correct. So this is how it looks like. So that I mean, I took all of the factors that were in here and I put them part of the definition of y, because they're just rescaling. That's exactly what we do. We call it a rescaling of the problem. The only thing that comes out of it in this case is x is actually the ratio of omega over omega naught. So if I'm changing omega, I'm actually changing x, okay, to these tunes. And if r in this case is all of the other terms that have to do with the resistance. So since I rescaled my problem, now I can graph it, knowing that the frequency cannot be negative. Come on, why is this? Oh, it's working. Finding difficulty with this expression. This is the resonance curve, by the way, that you probably have seen in chemistry and somewhere else also. So I'm going to start with omega visible being always positive. So I'm going to go to large quantities of omega. Let's say, for example, omega equals to 20, for example. And I know also this is a strictly positive function because it's actually, it's always positive because the numerator is positive, denominator is positive. And I'm going to stop it in here because this is 2. So maybe I stop it at 1.5. No, let's make it 5 or something like that, okay? Because I'll tell you my reasons for it. So this is how the function look like now. Let me change the lower limit to something that where the resistance is never equal to 0. At most, it's 0.1. And let me make this value in here at most to be, because if I divide it by, no, let's make it 0.2. Because if I divide by 0.1, it's going to be 5. So let's make this one 5.2. And now I have my curve. Okay. So if I have low resistance, this is the effect of this. This is a very sharp resonance curve in here. Okay. This is the response. This is the current in the signal. And the voltage did not change. V is not changing. Remember, we're scaling with it. The only thing that is changing is the frequency itself. This is where it peaks. It peaks around 1, actually. This is 1, 2, 3, and 4. And 1 is x equals to 1. That means omega equals to omega naught. So during that frequency omega, namely where they become in phase, then the signal is at its most. And it's at resonance. So it's a very, very strong signal. When the resistance now becomes too big, this broadens and the peak drops, and actually the maximum shifts a little because of this R. So if you have 5.2, look at it, right now it's near 1 and it's very high. So if I bring it down, the maximum is actually has shifted a little. It's not exactly at 1. And it has broadened, as I said, and the intensity drops with the higher frequencies, with higher resistance. So if I move further, you can clearly see now that the peak has shifted completely from 1. And the curve now does not resemble any of that of resonance whatsoever. So if I bring the resistance to even higher values, this is how the curve looks. So if you have broadcasting stations, one of them broadcasting at this frequency, another one broadcasting at another frequency, a third frequency, of course, you have to rescale according to their own frequencies. And in this case, omega is fixed from the broadcasting company. The broadcasting company is the excitation. The broadcasting company is sending a signal that is exciting your antenna, and your antenna has an omega coming from outside. And it's you now who has to change the value of C or L. Most of the time it's C. When you play around with C by doing those dials early, I mean, at least in the old days, your omega naught is the one that is changing. So your peak now is moving from point to point to point. Now you are receiving it at this signal. If you change your omega naught, and let's say there is another broadcast station at this frequency, you're going to pick the other one, and so on and so forth. So that is how resonance works, and that is how it works actually in sending and receiving signals. So this is signal reception. Now think about it this way: because we only have one omega naught, we really don't have a problem. If the circuit has more than one omega naught, and natural frequencies for coupled systems, they become more and more. So you could have more peaks in here in the curve, and each peak will be around a specific natural frequency. The resonance curve is a very powerful curve, okay? And I hope you guys can see it from the graph in here and appreciate the power that it entails in it, just by playing around with the frequencies only and nothing else. Don't change the intensity. You can have a response that could be very strong or very weak, depending on how far you are from the resonant curve. Okay? Does this analysis make sense to you guys? I know it's discussed in the book in about a page or something. Yes? No? Maybe? Okay, very good. So let's get into the applications of this stuff now. So the problems I thought we should start with, and we are going to do more come Wednesday next week, okay? Problem 37, 38, 39, and 40. So let's do 37. It says a coil has a resistance of 48 ohms. So R is 48 ohms. I know it has 3 sig-figs, okay? And a frequency of 80 hertz. So when they say frequency of 80 hertz, they mean F, they don't mean omega, okay? From here, since most of the calculations require omega, it's a good idea to go right away into omega, which is 2 pi F, which is 160 pi radians per second. This is, I see it common a lot, where people forget to do this step and they get into issues later on when it comes to reactance and problems like that. So this is actually an essential step when it comes to this one in here, okay? And if the question was asking you to what frequency something, then you're going to, at the end, go back into the other way around, okay? The voltage across the coil leads the current in it by 52.3 degrees. Determine the inductance of the coil. So it's just really mainly in this case, we don't have capacitance in here. We have RL only, okay? Because this is a coil. They tell you specifically it's a coil, so you have an inductance. So this is what you infer from the language when you read stuff, okay? So in this case, we know that tangent of phi is equal to XL minus XC over R, okay? And you know that XC is equal to 0. There is no inductor, no capacitor in this case. So in this case, the expression is just XL over R, and XL is just omega times L divided by R, and they gave you the angle in here to be 52.3 degrees. So from here, you can find what the value of L is. L should be equal to R divided by omega times tangent of phi. So in other words, R is 48, omega, I wrote it to be 160 pi, times tangent of, they gave you phi, 52.3 degrees. So you plug in 52.3 degrees. Okay, this is straightforward, okay? Here is the deal. When you are on a calculator, let me stop sharing and share with you this thing in here, because this is actually toward the end of the semester and we're going into exams and things like that. This is a common mistake that a lot of people fall into also. Please do not fall in it, okay? It's really a nightmare to see you doing all of the analysis correctly, but you get numbers all over the map, which later on will have implications everywhere. And the problem has to do with making sure you're working with the correct mode for the calculator. And I know I made a big fuss over it in the morning with another class. So hopefully also you two do not fall in that trap. Since they gave me the angle in degrees, and I really don't feel like in the mood of changing it to radians, so I have to change this one to degrees, okay? This thing is not responding correctly. It's my computer now. She's thinking. Okay, so it changed this to degrees. So now I'm going to go back into the calculator. I can do it now easily. But the point being in here is, no, it's still not responding. Man, what's going on today? Do I have anything going on this computer? So what I need in here, it says 48 ohms times tangent of 52.3 degrees, okay, divided by omega, and omega is 2 pi, which is 160, because F is 80 hertz, so it's 2 pi times 2 times 80 is 160 times pi, and that's it. That's what the denominator is, so we're in business now. So this is 0.123 Henry, or 124 Henry, because remember, I round up in this case. And there are 3 sig figs, so share back in here. So L is 124 millihenry. Okay, makes sense? Straightforward, isn't it? Okay, very good. This is so simple that even I can do it. I don't have to be an engineering student to have this. Okay, so another thing to check things around in here is to calculate the impedance in here, because the tangent in this case should be more than 45 degrees, so it has to be positive in this case. Remember, in the diagram that I wrote earlier, let me go back in here, when we were doing the resonance, when we started with the resonance, when it was in the phase space, I know we plotted it. Where is it? No, not that one. Not the RMS. Here. The phase is positive in this region when the inductor is winning. The phase is negative when the inductor is losing, in this case, in this situation in here. Okay? Well, in this case, capacitor, a capacitive circuit in here. So this is an important aspect in here. Not only that. Okay, yeah, that's basically in terms of the signs in here. Let me continue with the other problem that I promised we have to do in here, because we have quite a few problems to discuss. Problem 38. I hope you guys are writing. You're not just watching me do things, because it's really you're going to miss a lot on a lot of things if you do it that way, and you will have a hard time understanding what to do when it comes exam time. Okay, so problem 38. Problem 38, in an LRC circuit, series circuit, the phase angle is 53 degrees. So they gave you phi to be 53 degrees. Phi is 53 degrees. 53.0 degrees to be more specific, because they want you to have 3 sig figs in the problem. Okay. And the source voltage lags the current. That means the current is actually ahead of the voltage. Here is the problem. The voltage, remember, on the inductor itself, just focus on the inductor and you'll understand everything what it means. It's LdI over dt, which when I did the math, everything was the same except plus 90 degrees if it's purely by itself, nothing else, okay? So actually the voltage in this case is ahead of the current by 90 degrees. But I know from the problem, it says actually it's lagging. So whatever it is, overall the voltage is lagging. That means it's a negative number. So that means phi should really be, according to this thing, be negative 53 degrees and not positive for 53 degrees. Had it been that the overall voltage is ahead of the current, then in this case it's a positive. Since they say specifically, and the source voltage lags the current. So this phi should be a negative number. That's what that word means. I cannot emphasize how important the verbiage are in every single problem. When you're looking at a problem, do not just look for numbers and formulas. Look for the words in between, because they mean a lot, okay? This is one of them, okay? And then it says the resistance of the resistor is 300 ohms. So they gave you R, 300 ohms, okay? And the average power delivered by the source is 80 watts. So P average is 80 watt. All of these things have 3 kicks in them. I'm not writing the other 0, but I assume you know that. What is the reactance of the inductor? So we need XL. We need XL, okay? Here is what we know. We know tangent of phi is equal to XL minus XC divided by R. Correct? And we don't know what XC either is, but phi is negative number in here, okay? We know that phi is a negative number. We also know the power P on average, that's what they gave us. It's V RMS times I RMS, okay? Or if you want to, it's R times I RMS squared. Why? You're saying, because we wrote it also alternatively as R, what is it? The current I is equal to actually, what is it? V RMS, or V RMS is equal to Z times, oh, there is a cosine of phi in here. I'm sorry. There is a cosine of phi in here that we need that. That's what this expression, I mean, it's a little bit too early for it. Here is the expression. It's V RMS times I RMS times cosine of phi. Well, V RMS is Z times I RMS. So this is actually equal to Z, because remember, I just wrote the expression up in the expression in there. So V RMS, I can also write it as Z RMS, Z times I RMS. Okay, here's the deal. Because I RMS, I wrote it up there, and it said any I with any symbol in it, exactly what I wrote it here, toward the bottom. Any symbol in it, just put your symbols as you wish. Is an RMS or a max, it doesn't matter. Here. So V is equal to ZI, basically, okay? Because I is equal to V over Z. So that's the expression that I have in mind in here. So, but I'm using the RMS right now, the root mean square, or did they give us the actual voltage? No, they did not give us the actual voltage. It doesn't matter. One of them, we can find it. So now it's Z times I RMS times another I RMS. This is coming from V, by the way, times cosine of phi. And remember the ratio of the impedance in here. So this is R times I RMS, and this is Z times I RMS, and this is the angle phi. The cosine of this angle is equal to Z times R is equal to, basically from this math in here, if you do it correctly, this is XL minus XC times I RMS. This one, the adjacent divided by the hypotenuse, and the I RMS cancels, it's going to be R over Z is equal to cosine of phi. In other words, Z times cosine of phi is just R. So this is R times I RMS. The whole point of writing it this way is actually so that it looks like it's Ohm's law. Okay. So from here, we have an expression for I. Okay. And since we have an expression for I, oh, I forgot something, because now I'm kind of, I'm sorry. XC was given. You guys need to help me here. XC was given to be 500 ohms. Okay. XC was given and R was given. So this equation would be enough to find XL. Because we know what XC is, we know what R is, we know what the angle is. From here, we can find what XL is. I was wondering, what am I going to get this expression here? So we know XL minus XC is equal to R times tangent of phi from that expression, from this one. And from here we have XC, so it's XL is just equal to XL is equal to XC plus R tangent of phi, and XL, because that's what they're asking, is 500. The tangent of a negative number is a negative value, so it's minus 300 tangent of 53 degrees. That's it. So it's easy. And I thought we're going to go into solving a system of equations and doing stuff like that. Sorry about that. Okay. So that's why it's very important to read all problems from the beginning to the end. But don't forget that that phi is not a positive number. It's actually a negative number. That's all. Since I am doing this one in it's 101.888, so it's 102 ohms. 102 ohms. So that is how much XL is. Okay. So this is the value of XL based on just on the angle in here, okay? Because the angle is, they tell you it's lag, so it must be a negative number. Since they gave us XC and we know what R is, and the only unknown in this equation is then XL, so we're in business. Then we found what XL is, so we're good. Okay, so this is the reactance. So it's very important to look at it this way. So I have 102. This is XL. I have 500, which is XC. It's clearly divided by 300, it's clearly this number is less than 0. Okay, so it is good. So everything is good because of the fact that in this case, the voltage overall lags behind the actual current, meaning that this capacitor is bigger in impedance and reactance than that of the inductor. That's all. That's all there is to it. That's how you find it. Make sense? Yes, very good. Now, just to continue with the other calculation, that should give me IRMS. So I already made the case for the other one, for this expression. Since they gave us a power and know what R is, we can find what the IRMS is. Since they told us what is the current amplitude in the circuit. No, they don't want the IRMS. They want just the current, which is fine since we can find it. The current amplitude is just multiplied by square root of 2. We're in business, okay? So IRMS is equal to square root of the power over the resistor. And that means I max, which is the amplitude, is square root of 2 times the square root of P average divided by R. In other words, it's going to be square root of 2 times how much the power said? They said it's 80 watts, and the resistance is 300. So according to my calculator, it's going to be square root of, open parentheses, 160 again, divided by 300. Of course, under square root, it's going to be 0.30 watts. 0.30 amps. So I max. This is the max. Obviously, this is an alternating current, okay? It's going up and down. So it's between 0.73 amp and negative 0.73 amp. So that is a cosine function, okay? Or a sine function, however you want to call it. And what is the voltage amplitude of the source? Since we found the voltage amplitude, we can use this same expression in here that I've been using, namely the voltage amplitude, or Vmax, is equal to Z times Imax. And Z is the square root of 300 squared plus 102 minus 500, the whole thing squared, times this number that we just found, 0.73. It is very important you follow the steps, okay? This is very important you understand that this is Z and not anything else, okay? So it's going to be, again, square root of the resistance squared, which is 300 squared, plus, open parentheses, 102 minus 500, the whole thing squared, and close the parentheses of the square root, and multiply the answer by 0.7. Let's multiply it by the previous value, okay? It's much easier. Multiply it by this number. So it's telling me V max is 363.9 or 364 volts. 364 volts. Okay. So this is problem 38. Make sense? It is very important that you guys review these things, okay? It is very, very important that you guys go through these things on your own, because it really helps a lot in understanding them. When you read the problem again and you go through the steps, you have it on YouTube, you go and look at it, and then you go through it, and you have a full understanding and check mark on every single question. I think I will be confident at that time that you know what you're doing. If not, I would be very much eerie about this thing in here, because it's really a lot of things to be done. Okay, problem 39. Problem 39, it's similar. It says in RLC circuits has C, so they gave you C to be 48 or 4.8. I know I have 3 sig figs microfarads. And they give us L to be 520 millihenry or 0.52 millihenry. I mean Henry already, and the source voltage to be 56 volts, 56.0 volts. So this is the V max, okay? That's what the amplitude means. The source is operated at the frequency of the circuit. That means F is equal to F naught. In other words, the omega of the source is the same as the omega naught. In other words, it's 1 over square root of LC. We are at resonance. At this point, we are right in smack in the middle when XL is equal to XC. So that's what all of this language means. So they didn't give you anything else except the statements. You know exactly what frequency is. Okay. The source operates if the voltage across the capacitor has an amplitude of 80 volts. So across the capacitor, VL is 80 volt. Okay. What is the value of R of the resistor in the circuit? Okay. So we know VL is equal to basically IRMS times XL. XL times IRMS. Okay. I'm sorry. No, this is VC. They gave us VC. This is across the capacitor inductor. Capacitor. This is VC. So they gave us VC to be XC times IRMS. Okay. And we know that XC is equal to 1 over C omega times IRMS. Okay. From here, we should be able to find what the IRMS is of the circuit, because we know what omega is. Omega is actually equal to 1 over square root of LC. That is given. And this is C, the capacitance. That is given. So from here, it's equal to square root of L. I'm sorry. Yeah, square root of L over C. When you cancel, because you have a C in here, which is square root of C squared, and this one has square root of LC in the numerator, the C cancel one of the square roots, and you'll be left with this expression times IRMS. So from here, we can find what the IRMS is, which is 80 volt divided by square root of L, and L is equal to 0.52 divided by C, and C is equal to 4.8 times 10 to the negative 6. In other words, this is equal to 80 times the square root of 4.8, 10 to the negative 6 divided by 0.52. So how much is the current in here? Let's find it. No, this is not IRMS. Again, I fell into exactly the same mistake I was trying to tell you to avoid. This is the actual amplitude. So this is the max. This is the max. This is the max. Because this is the max voltage, they gave you the amplitude. This expression works for the amplitudes or the RMSs. So again, this is the max. Again, I fell exactly where I told you do not fall into. I'm glad that I did, honestly, because you really need to recover from this type of mistakes, okay? So when you do that and it happened to you, at least you saw it happen to me so that you say, okay, I don't want to fall into the same trap, because when I'm grading these things, usually I put the solution way ahead of time. So I will know you did it wrong. So please don't do it wrong. Don't do it like I do, like I did in here. So I just plug in the numbers in here and it gave me a current of 0.43, 0.243. Obviously, they didn't ask me for the current. They asked me for something altogether. They asking me for R. But since I know what R is now and what the overall voltage is, so I can find what the R is, because let's think about it. At resonance, Z is equal to R. Remember, it's square root of R squared plus XL minus XC squared. But at the resonance, these two are equal. So the only thing that is left is R now. That is what Z is. So the overall voltage now, I know what it is. The overall voltage, V, this is the max value overall, which is given to be 56 volts to begin with, is equal to the overall current times Z. So it's Z times R, Z times I max also. I just found what I max is. And this Z is equal to R at resonance, so it's R I max. From here, I can find what R is, and that is V max over I max. This is 56, and the other number I just calculated to be 0.243. So from here, we can find what the resistance is, which is 56 divided by, since I have it still in the calculator, divided by that number. So it's giving me 230 ohms, 230.4 ohms, okay? Since I have 3 sig figs, so it's 230 ohms. Make sense, this problem? So it's kind of a long way, thank you. It's a long way, but it's really, hopefully you guys see it, since they gave you the voltage across the capacitor, and you know what the capacitance is, and they tell you it's at resonance, so you know what omega is. So from here, because omega is 1 over square root of LC, and you have C, and you have the L. So in this case, you can find what the current is, the max current is, and you use it then for the entire circuit where the entire voltage, which is given to you, V max, so 56 volts, is ZI max. Since you just found what I max is, you can find basically what Z, but Z at resonance is exactly R. So in this case, you just find what R is. So that's a question that I want you to find. Okay, very good. So we move on to the last problem for today on the list that they gave you, and there will be more, as I promised. So we did 39. So the last problem in the list is 40. Problem 40 basically gave you a circuit, 5 infinite impedance voltmeters. Impedance and reactance are used, and resistance are actually used exchangeably because they have all the same units, okay? Voltmeters calibrated to read RMS values. So in this case, everything that is given in here is an RMS, not in max, okay? Are connected as shown, and they give you a circuit. Basically, you have, let me draw the circuit. So you have a resistor, you have an inductor, and you have a capacitor, and you have a power supply in this case, which is an alternating power supply, and you have a circuit that looks like this. So V1 is connected in here, okay? V2 is connected in here. V3 is connected in here. V4 is connected in here. And V5, which is the overall V actually, between points A and B, is here. Okay. So that is basically what they gave you. And they gave you the numbers now. They gave you R is equal to 200 ohms. Okay. And L is equal to 0.400 Henry. And C is equal to 6 microfarads. Or 6 times 10 to the negative 6 farads. Whereas we have V, this is the power source V, okay? So this is the V in here. V, which is the actual V, not the RMS. This is the V max, is 30 volts. Okay. What is the readings of each voltmeter for omega equals to 200 radians per second? That's case 1. And omega equals to 1,000 radians per second. Okay, the expression for this one in here, first of all, I need to find what I is, I max. Okay, since we really need IRMS to multiply it by these things, we're going to find the IRMS because all of these devices read RMSs. So IRMS is going to be V max divided by square root of 2 already, divided by Z. And Z is square root of R squared plus omega squared, omega L minus 1 over omega C, the whole thing squared. Okay? You have V max, 30 volt. You can punch in square root of 2. You have R, which is 200 ohms. You have L, which is 0.4. You have C, which is 6 times 10 to the negative 6 farads. You have 2 values for omega. There is a case for omega equal to 200 and the case for omega equal to 1,000 radians per second. So there are 2 values for omega, not just one. And then the voltage across this one is going to be R times the IRMS. So across in here, it's going to be just R times IRMS, whatever you find from that calculator. In here, it's going to be omega L times IRMS. In here, it's going to be 1 over omega C times IRMS, whatever you find from there. So I'm really looking at these voltages now. This is V1, V2, and V3. This one, though, is going to be omega L minus 1 over omega C times IRMS. And this voltage now is actually should be this voltage 30 divided by square root of 2. Do it this way, you will find something weird, okay? First of all, these numbers are actually the difference of 2 numbers in here, okay? And this one is not necessarily the sum of all of the 3 of them. As a matter of fact, you see it from here, it's a Pythagorean theorem. So I'm going to leave it for you guys to go through this exercise. If you have difficulty with it, please let me know. First of all, you have everything in the problem. There is nothing missing in the problem. You have the L, you have the C, you have the R, and you have the V max. In order to find V5, all you have to do is take V max and divide it by square root of 2, because they tell you specifically that this voltmeters read RMSs, they don't read maxes, okay? So that is V5. Now I need to find the IRMS everywhere in the circuit because I need to calculate based on it. So I need to use this relationship to find the IRMS. Once I'm done with that, then I can find the V across the resistor, the V across the inductor, the V across the capacitor, and the V across both of them, and the last V everywhere else. So these are the RMS values that are reading in here. This is nothing else, okay? So when you find it in here, it's going to be an absolute value, by the way. If it's negative, that means you're looking for the maximum in this case, okay? So technically, this should not be like this. It should be an absolute value, okay? So that's the end of it. because one of the omegas is going to be positive and the other omega, for the omega which is equal to 200 radians per second. Let's find where omega naught is to see if this is true. Omega naught for this circuit is 1 over square root of LC, and L is 0.4 from the calculation, times 6, 10 to the negative 6 under the square root. So omega naught, the cutoff for the resonances, which is critical usually for any problem that deals with this type of thing, it's the square root of 1 over, open parentheses, a bunch of numbers, 0.4 times 6 times 10 to the power negative 6, and close the parentheses, and close the second parentheses, and it's 645.4. So in other words, 645 radians per second. So this frequency is less than it. So this is low frequency, in which case this number wins. 1 over omega c should be, this number would be negative, okay? If it is for 1,000, this becomes a small and this becomes big. So this is going to be positive, okay? Because the cutoff frequency, the resonance frequency is 645 radians per second, and they gave you two frequencies, one below and one above. Okay? Do you guys know how to proceed with this problem? Okay, glad to hear that. For the others, please try it, and if you find that it is an issue or there is an issue or there is a problem with this problem, we have plenty of time to discuss these things. As a matter of fact, I'm looking at Wednesday of next week, the Wednesday after, and if need be, and at this point, probably not, but if need be, we have that Wednesday morning too, to discuss things, okay, to go through these things. So in other words, if you feel like you need to meet on a one-to-one basis, I'll be more than happy to do that, to discuss these problems. If you feel that you want to actually go through the entire class and have a discussion similar to this one and everything makes sense to you, that's fine too, because I really want you to be at ease with all of these problems. Good?
Professor, I have a question.
Uh-huh.
Yeah, like I have been looking at Canvas, but like, are you going to post the lectures? Because like, I'm not able to find them.
They should be on Canvas under discussion sessions of every class we do. We have, I record the class and I post it on Canvas.
I did not find it for the last week or the week before it.
Did not, I'm sorry, hold on, let me check again. I did not upload it, that's gonna be, okay, hold on. The one for the 17th, which was last Monday, if I'm looking at unit number 12 and the discussion, it says there, it's there. That is at least the last one. Which one you're missing, do you know?
I'm gonna email you the one that I'm missing, because like I think
That's
there's.
Because if I did forget, please let me know, guys, because usually what I do in here is after the class is over, about an hour to 2 hours later, they make the video available for me. So I upload it to YouTube and provide the link for that on the discussion session so that you see all of the things that happen in there. So if I forgot, please let me know, no problem. We're going to find it and then upload it. Good?
Good, thanks.
No problem. Okay, I see you guys. We have a 2 o'clock lab, which is going to be our last lab. So I'll see you guys in probably, what, 45 minutes?
Yeah, sounds good. See you then.
Let me stop recording and I'll see you later. Okay, guys.